All right. Welcome to chapter 10, our final chapter. Sounds like we've just had like a series of movies, and this is the final chapter. So today we basically have no math. I don't think there's really any math at all. So we basically have no math today. So what we're going to do is 10.1. 10.1, you're learning a little bit of vocabulary and just learning a little bit of new stuff here about that. And then 10.2, we're going to talk about what hypothesis testing is. Um, but we're not going to do the math behind it. We're just going to talk about what it is and what it looks like. And then on Thursday, we'll do all the math. So that's the plan, and that'll get us through all of the material in this class. Then Tuesday next week, our class will just be drop-in office hours. It won't be any new material. So all the new material will be done this week. And you may have noticed, and if you saw my email, you would definitely know, I opened everything up except for the final test. Everything else is open. So the all of the materials for review, those are open. All the final project assignments, those are open, and everything but the test. The test obviously won't open until Tuesday of next week. But that's it. We are in the home stretch for sure now. So today, as I said, we're going to talk about null and alternative hypotheses. We're going to talk about what they look like, how to write them, what they mean, and then we're going to talk about type 1 and type 2 errors. And we're going to talk about how you would write your conclusion to a hypothesis test. And then we're going to talk about pretty much what the hypothesis test looks like. That's what this explain the logic means. We're going to talk about what it looks like and the different ways that we test a hypothesis. So that's what we're going to do. And there's not really any math, as I said. The math will be on Thursday. We'll do all of the math stuff. So 10.1, that assignment, isn't going to have any math in it at all. It's all like vocabulary and setup. Okay. So a hypothesis, it's kind of the same thing as it is in science, where you're making a statement about what you believe will happen or what you believe you are going to see. And then afterwards, you're going to set about trying to prove it. So we make a statement about a characteristic of one or more populations, and we're going to look about like a single population parameter, because you can make a hypothesis about a lot of different things. I could say that I think the mean is greater and the standard deviation is less. And I mean, I could give you like 3 or 4 different things, but we're going to do one. We're going to say something like, I believe that the percent of people who are in favor of the death penalty is smaller today than it was previously. Or you can say, I believe that the number of people with, or the percent of people without a landline is greater today than it was previously. So we're just going to take one characteristic and do a hypothesis surrounding that. So here's a couple of different ways that our claims can be written. So one of our claims, in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes this percent is different today. So the hypothesis part is this part right here. The researcher is hypothesizing that the percent of people who regularly volunteer is different. He's not saying if it's greater than or less than, he's just saying it's different. So that is one way that it could be written. So this one right here, according to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. This part, whoa, I know my pen disappeared. This part would be my hypothesis. So they think that the average length of a phone call is greater today than whenever they did this 2006 study. They believe that it is changed and that it is greater. So that would be the hypothesis. Right. So another one. Using an old manufacturing process, the standard deviation of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. So they have some new equipment, and they believe that the new equipment has decreased the standard deviation. And so my hypothesis is that the standard deviation has decreased. That would be my hypothesis right now. So these are just statements. We're going to build on these statements by writing out what, like using our own notation for hypothesis testing. And we're going to do that in a minute. And I'm going to show you what those look like. So when we are doing this, we're using sample data because you're not going to make a hypothesis if you have all of the data in the world. If you have the population data, then we don't need to hypothesize because you know it because you have the population data. So we're using sample data, just so you know. So here's what hypothesis testing is. So we take sample evidence and probability, and we use it to test statements regarding a characteristic. And you just saw that it says like they think the standard deviation is less today. That's what we would test. We would take a sample. After we hypothesize, you would take a sample and you would test that sample. And basically, so I'm going to back up just a little bit. So last unit, you remember us saying, maybe it was actually chapter 8. Chapter 8, we talked about, oh, if I have a sample and 2 out of 20 have this characteristic, would that be unusual? You guys recall statements like that? So that's essentially what we're doing. So we are basically going to be taking a confidence interval, which is what we did in chapter 9, basically taking a confidence interval and testing our sample. If our sample is outside of that confidence interval, then we are proving, not prove is not the best word, but showing that our hypothesis test is true. So you're just testing a sample against your hypothesis or your confidence interval. That's all we're going to be doing here. However, we're going to be using high confidence intervals that are one-sided, right or left, and you'll see that in a minute. But that's essentially, we're taking what we did in chapter 9, building a confidence interval, and then testing it, testing a point to see if it's inside or outside of that confidence interval. And that's going to tell us whether or not our hypothesis is true. That's essentially what's going to be happening here. So we're just adding a tiny little bit to chapter 9. Okay. So here's what we do with hypothesis testing. You're going to make a statement regarding the nature of the population. So just based on, it's kind of like an educated guess. It's like, as more and more people get cell phones, and as those who are like anti-cell phone get older and older and unfortunately die off, we're going to have more and more people that have only landlines. This is in my brain why I think the percent of people who have only cell phones and no landline is higher today than it was previously. So that would be just based on what I think, based on what's going on in the world. Then I'm going to collect my evidence. After I make my statement, I'm going to collect my data. So I'm going to collect a sample, and then I'm going to analyze that sample to see if the statement that I made is plausible. The hypothesis that I made, is it plausible based on the evidence? That's what you're doing for a hypothesis test. This is very much like scientific method type. If you're a sciencey person, you can see the scientific method all in here. So hopefully you can appreciate that. I know a couple of you are pretty sciencey. All right. So our null hypothesis, which we use this right here, we call that H naught. That little sub-zero, we call that naught. So this is H naught, the null hypothesis. This is what we are saying is true until we prove it isn't. So until we prove it's not true, this is the evidence that we have. So it is our statement of no change. We'll always have an equal sign. It'll always have an equal sign in it. And this is what we're saying is true until we prove it's not. That's our null hypothesis. Then we have our alternative hypothesis. The other way that you might see it written is H sub A. These are both identical. They're both mean the same thing. We're trying to find evidence to support the alternative hypothesis. This is what we think is true. I think that the number of people who are have no landline is greater than today. That's where I would put it. My alternative hypothesis, I'm saying I think that it is larger than this. So you're going to have a greater than, a less than, or a not equal to here. I'm going to expand on this, don't worry. So that you never have an equal on the alternative hypothesis. So it's either greater than, less than, or not equal to. So this is what I'm trying to support. This is where I'm putting my guess, my hypothesis is on the alternative hypothesis. All right. Questions yet? Are we still hanging in there? Okay. All right. So here's what they look like. So if I say the words different than, I'm going to write those right there. Different than, or just different. If I say the word different, it's a two-tailed test. And we will use our alternative hypothesis will be say not equals. If the word different is in there, it's a two-tailed test and it'll say something, it'll say the word different or it'll have a not equal. What that looks like, I'm going to draw this somewhere. What it looks like is, here's my confidence interval. And if my sample, if the information regarding my sample lands out here or out here, then I have shown that my hypothesis is true. I have evidence that my alternative hypothesis is true. If I land anywhere outside of that confidence interval, this is the confidence interval in here. If my sample information lands in there, then I have not shown my new hypothesis to be true. That's for a two-tailed test. For number 2, you're going to see the words less than or decreased or something like that. It'll say less than, it'll say decreased, or something to that effect. You'll see that with a left-tailed test. With a left-tailed test, draw the picture. With a left-tailed test, we're saying less than. So this area, if it's anywhere up here, then you don't have enough evidence to support your alternative hypothesis. If your sample lands out here, then you have evidence to support your alternative hypothesis. Okay, finally, we have the right-tailed test. The right-tailed test, you'll see greater than or increased, or some words that mean something like that. And it's going to look like this. So this right here, if your sample lands here, you do not have evidence to support your alternative hypothesis. However, if your sample lands out here, then you have evidence to support your alternative hypothesis. Questions?
I have a question.
Yes.
I just want to kind of help my brain understand this.
Okay.
So all the places where you pointed to when it's outside of the green area, that's the H1.
Right.
So you're proving that the H1 is correct.
Right.
Okay. Okay. Thank you.
And if it lands in the green, then you don't have enough evidence to support your alternative hypothesis.
Great. Thank you.
You're welcome. Because, we're all about evidence. Anyone else before we move on? All righty then. Let's do this. Okay. So my null hypothesis is status quo. So this is our statement of equality. So this is like, for example, if I said, um, trying to make something up. Let's say 68% of all people believe that cell phones should be banned in school. Say there was a study 2 years ago that said 68% of people believe that cell phones should be banned in school. That would be my null hypothesis. The previous evidence that I have, the previous numbers I have is my null hypothesis. So I would say my H naught is that the proportion of people that want cell phones banned in school, 0.68. This is true until I have evidence it doesn't. And I'll say now 2 years later, I think that's changed. I think it's different today. I didn't say it was higher or lower. I said it's different. Therefore, I do the not equals. So notice both of them have the P and both of them have the 0.68. The only thing that's different is the equals and the not equals. This sign changes. This is always equal. This is always equal. And this one is going to be either less than, greater than, or not equal to. Those are the three things possible right there. So we assume this is true until we have evidence to support something different. We're going to assume that that is true in the beginning. All right. Are we ready? Good. Okay, I'm going to move on. All right. So let's write our null and alternative hypothesis. It's going to show up on the next screen, but I just feel like talking through it and writing it out is more helpful. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes this percent is different today. Here's my trigger word right here. This is my trigger word right there, different. Different means two-tailed test. So this is a two-tailed test. Two-tailed test because it says the word different. So my null hypothesis always assumes the information is given, that is given. So I would say that my P equals 0.62 because it is true until I have evidence otherwise. My alternative hypothesis is what I'm going to try to prove. So the P is not equal to 0.62 because it says different, could be greater than, it could be less than. I'm just saying it's not equal to. All right, questions before we move on to the next one? Okay. Yeah, see, they give you the same thing, they just give you a lot more words. All right. But I mean, it's good that that's there if you print out the PowerPoint. It's good that it has that other screen. Right, so according to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes the mean length of a call has increased since then. Here's our trigger words. Has increased. So we're saying that we think it is greater than. So greater than is to the right of on the number line. Therefore, this is a right-tailed test. Because it is to the right of my confidence interval. So once again, null hypothesis just states what we were given. So we think that the mean is equal. equal to 3.25. Mu is equal to 3.25. We are saying we believe that the national average is 3.25 or whatever. We think the population is 3.25. My alternative hypothesis, I think it is greater than 3.25. Now, I haven't taken a sample yet. I haven't done anything yet other than make a guess. I believe this is true. That's all I'm saying. I think it's probably true because most people don't make phone calls unless what they have to say is too long to text these days. Those are the only phone calls I make. They're the ones that are like to a doctor's office or something, or if it's too long to text. I see. You agree with me, don't you, Hannah? So then you have to talk longer than three and a quarter minutes because you're like, I'm not going to text this whole thing. See? Yeah, exactly. Somebody calls you, you're like, I hope everybody's okay. Whenever my daughter calls me, I'm like freaking out because she doesn't make phone calls. Like, uh-oh, something's wrong. Yep, see, somebody died. But no, my other daughter, she calls me all the time. I'm like, why are you calling me? So there you go. And I'm Gen X. You'd think that I would actually like to get the phone calls. No, those are boomers. Boomers want phone calls. Okay, moving on. So this is all the stuff I just said. All right, finally, using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. Trigger word right here, has decreased. Decreased is less than. Someone texts you after calls you after you text. I know, seriously. How dare they? Okay, so now our null hypothesis, we're using standard deviation, so I'm going to do sigma. Remember, it's always equals 0.23. You could write ounces there if you want. It doesn't really matter. You can put the ounces there. It doesn't really matter. So 0.23 ounces, my alternative hypothesis, because it has decreased, it's going to be less than. Your 10.1 homework is going to have you writing these. Actually, it's going to have you like choosing the correct symbols and all of that. So that's what your 10.1 homework is going to look like. And it's going to ask you if things are right-tailed. Oh, this is a left-tailed. Sorry, I forgot that part. Because it is less than, you are looking to the left to see if it lands to the left. That's why it's left-tailed. So yeah, you'll be asked, is it right-tailed, left-tailed, or two-tailed? And you'll be asked to write out the null and the alternative hypothesis. 10.1 should actually be a pretty quick assignment. So you don't have to calculate anything. Questions before we move on? Feeling groovy so far? Okay. All right, this is just what I already just said. All right. So here's the different outcomes. So this is type 1 and type 2 error. You will be asked if something is a type 1 or type 2 error, and you will, I'm going to tell you that I mess these up all the time myself. Thankfully, you have notes. I go pretty lenient on these. And there's only a couple of problems on my open math. And I believe there is going to be one of these on the test. So the most important thing with the one on the test is it asks you, what would a type 2 error be in context of the problem? If you're asked for something in context of the problem, you have to mention what the problem is about, what the story is. Like, for example, if I wanted to know what a type 2 error was with regards to the cell phone calls, you would have to mention the cell phone calls. So make sure that when it says in context, that you are mentioning the story, whatever story they give you. So the 4 different outcomes. If you reject the null hypothesis, these are the words, reject the null hypothesis when the alternative hypothesis is true. This is good. If you find out that the alternative hypothesis is true, we reject the null hypothesis. Do not reject, or the words I like to use are fail to reject. I don't care if you say do not reject or fail to reject, but please make it clear whether you are rejecting or not. Make sure those words are clear. You're going to be writing out a conclusion in your test. Make sure you're making it clear to me whether or not you're rejecting the null hypothesis. So if you fail to reject the null hypothesis when it is true, this is correct. If you determine that the null hypothesis is true, you fail to reject it. If you determine that the alternative hypothesis is true, we reject the null hypothesis. So we either reject or fail to reject the null hypothesis. We don't ever reject the alternative hypothesis. We don't ever fail to reject the alternative hypothesis. Our decisions are made against the null hypothesis, whether we reject it or fail to reject it. So if I rejected the null hypothesis, but the hypothesis was true, this is a type 1 error. This means you made an error. You rejected it when you shouldn't have. This is called a type 1 error. If you fail to reject, but you should have rejected, then this is a type 2 error. Questions about type 1 and type 2 errors before we show some examples? These can be a little bit confusing. So having your notes with you, definitely this page when you are taking your test will be a good idea because they can be kind of confusing. And I always forget which is which, like almost always. So if I don't have it in front of me, I'm not going to remember it. So I don't force you to memorize it. Notes are good. Okay. So let's talk about what a type 1 error would look like and a type 2 error would look like. So in 2008, 62% of Americans regularly volunteered their time for charity work. A researcher believes the percentage is different today. So I'm going to show you, I have them typed up here. So a type 1 error. So if I say that if I reject my null hypothesis, but the actual number of people that volunteered is actually 62%, then it's a type 1 error. So I would say if I reject the null, but shouldn't have. So I'm saying, I'm concluding that it is different than 62%, but it really isn't different than 62%. So the type 2 error, I am failing to reject. I am saying, hey, my evidence doesn't conclude that it's different than 62%. I'm saying it is still 62%, but it's different. Then that's a type 2 error. So fail to reject, but should have. Right. Makes sense? Questions? I think I might have another one. I do. Actually, I think I have both of them. I don't know. Right. So this is the cell phone calls. So they think that it has increased since then. So let's look. So type 1 error. So if I say that my evidence shows that the mean is greater than 3.25, but in fact that average length of a phone call is still 3.25, that's type 1 error. I rejected the null hypothesis when I shouldn't have. So type 2 error. So I'm failing to reject the null hypothesis. I'm stating a cell phone call length is still 3.25 minutes, but in fact it's longer than 3.25 minutes, then that's a type 2 error. So I'm failing to reject, but I should have rejected. I told you it's a little bit confusing, but if you just keep that in front of you, and even if what you type is kind of bumbled a little bit, I'm probably still going to give you credit for it. If you put in a good effort, you're probably going to get credit for it from me because it is a confusing thing, and it doesn't matter when it comes to the math. So if it doesn't matter when it comes to the math, then I'm going to be pretty lenient on it. All right. So the probability of a type 1 error is alpha. The probability of a type 2 error is beta. So if the assignment asks you what's the probability of a type 1 error, say alpha. If it says what's the probability of a type 2 error, you say beta. That's it. This might be the better screen than all the words. If you like these short little definitions, this might actually be better than that one with all the words on it. And I definitely don't care if you remember alpha or beta. But remember we were using alpha for our confidence intervals? This is the same alpha. This is that same alpha. It's just being used in a different context, but it is the same alpha. The amount of the curve in the tails is your alpha, is the probability of making that type 1 error. The amount of the curve inside your confidence interval is beta, and it is the probability of making a type 2 error. And don't worry, you're not going to be held to that. I'm not going to require you to give that back to me or explain it to me or any of that. There's a whole lot of super deep stuff that goes into these that you don't need right now. In fact, I don't even think you get them if you take Math 244, I don't even think you get them there. I think it's the 360 level math classes that you get that stuff. So if you don't quite understand the difference with alpha and beta, don't worry about it. It's not going to affect anything. Moving on, maybe moving on if it lets me. Okay. So we choose the probability of making a type 1 error before the sample data is collected. I will always give you alpha. I will always give you alpha. So don't worry about trying to calculate alpha. You'll always be given it. We call the alpha the level of significance. So if I tell you the level of significance is 5%, then that is your alpha. The probability of type 1 error increases and the probability of making type 2 decreases. It's a matter of, like, for example, this is my beta and this, and this. Oh, but this is alpha divided by 2, and this is alpha divided by 2. So obviously, if my um, if my confidence interval gets smaller, my alpha is going to be bigger. If my confidence interval gets bigger, then my alpha is going to be smaller. Obviously, right? Because we only have 100% here, so we've got to keep splitting that up. All right. This is important. We never accept the null hypothesis. We don't have the entire population. This is kind of like in science when you say things are theories. Even though technically you've like proven it's true, you you can't 100% say it's true because you can't sample every single thing that's out there and test every single thing that's out there. So you still call it a theory. So with hypothesis testing, we only took a sample, so you can't say this, this is absolutely true. So we just say that we fail to reject the null hypothesis. We do not reject or we fail to reject. I say fail to reject, but you can say do not reject. Either way is fine. It's kind of like we never declare a defendant innocent. We just say not guilty. So we don't ever say, we find them innocent. We find them not guilty. It's the same like premise there. We are moving along so nicely. I love this. And your brain's got to feel kind of good, a little bit of a break from actually making calculations. It's got to feel a little bit good. Even though I'm not nearly as good of a teacher of things that aren't math as I am with things that are math, in my opinion. Okay. So I'm going to show you what the wording would look like for these conclusions. We're going to write the conclusions. They give a lot more words than I give. I don't write as wordy conclusions as they do. So here we're supposing that our sample evidence indicated that our null hypothesis should be rejected. So I'm going to show you the wording of the conclusion. Look how long their wording is. The statement in the alternative hypothesis is that the mean call length is greater than 3.25 minutes. Since the null hypothesis is rejected, there is sufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes. Here's what I would say. There is sufficient evidence to indicate that the mean length of a cell phone call is greater than, this is not a lot fewer words, but it's fewer words, than 3.25 minutes. Therefore, we fail to reject. Wait, we reject, sorry. We reject the null hypothesis. So obviously, like word for word, you don't have to write it like this. But when you're taking your test and you're writing your conclusion, I would like it to look something like this. I would like you to I would like you to tell me what the evidence is, and I will explain that later. I would like you to explain how you know, and then I want you to tell me whether you reject or fail to reject. And since I haven't taught you yet how you know, we're not going there yet. But I want you to state how you know, and then tell me whether you reject or fail to reject. Make it really clear that you've rejected or that you've failed to reject. Because you can say, we do not reject. That's fine. If you don't like the words fail to reject. Questions on what I wrote or what they wrote? Okay. Let me do another one. So this one, the sample evidence indicates the null hypothesis should not be rejected. So this one is going to be fail to reject. So we're going to show the wording of that conclusion. Since the null hypothesis is not rejected, there is insufficient evidence to conclude the mean length of a call on a cell phone is greater than 3.25 minutes. In other words, the sample evidence is consistent with the mean call length equaling 3.25 minutes. I will write my way. There is not sufficient evidence to conclude that the mean cell phone call is greater than 3.25 minutes. Therefore, we fail to reject the null hypothesis. There we go. I just feel that, I mean, it's my opinion. You may feel differently. I feel that the way that I wrote it is a little bit cleaner, but you do you. You write it how you want it, as long as you're basically saying whether or not there's evidence to conclude that and whether you fail or reject the null hypothesis. Questions? Okay. We're on 31, slide 31 of 44. We're grooving right along. Do you need a minute? Are you copying it down? You're good? Okay. All right. We're on 10.2 if you keep track of those things. We just finished 10.1. So we are now at 10.2. All right. So a researcher obtained a random sample of 1,000 people and found that 534 are in favor of banning cell phone use while driving. So that would be your p-hat would be 53.4% or 0.534. Does this suggest that more than 50% of the people favor the policy? Or is it possible that that proportion could be less than 0.5%? Or sorry, 50%, 0.5. Would it be unusual to obtain a sample proportion of 0.534 or higher from a population who is 0.5 is their mean? So what I'm saying is, if I took a sample and got 534 out of 1,000, would that be unusual if the actual proportion was 50%? Would it be unusual? So that's what we are determining. So just because it's different right here doesn't necessarily mean that our alternative hypothesis is supported. What it means, I mean, what I'm trying to figure out is that 53.4% inside my confidence interval, or does it fall outside of my confidence interval? That's what we're testing. So if something is statistically significant, don't worry, you don't have to memorize this. You don't have to reiterate it to me. But if something is statistically significant, we are going to reject the null hypothesis, which means, so if I end up with something that would be unusual, if I have a sample that would be unusual, that is statistically significant. Generally, our rule of thumb is 5%, but really it depends on what your alpha is. So you may recall a long, long time ago when we had that women in the workplace thing where they had all those women applicants and they decided to use the 0.5% as their unusual amount. So they just basically changed the alpha. So they changed that alpha. So based on what the alpha is, that's how we determine if something is unusual. Sometimes it will be 5%, sometimes it'll be 2.5%, could be 1%. Whatever the alpha is, that's going to help us make our decision on whether something is statistically significant. All right. So the these are the pieces. We're not going to put it all together yet. These are the pieces. So what we're going to determine is we're going to use the standard deviation and z-scores to determine whether or not this would be statistically significant. So the first things that we need to look at, this right here, NP times 1 minus P is greater than or equal to 10. This 1,000 is less than 5% of my population, so we're good. So we can use our normal model. Those things need to be tested. So our mean, we say that this is our mean and this is our standard deviation. So what I'm going to do, so I'm going to say 0.5 plus 0.016 times 2. This is my 2 standard deviation rule, right? I don't even have my calculator. What the heck? I'm going to have to use my cell phone. I don't even know what I did with my calculator. Look at me being all unprepared and stuff. So clear 0.5 plus 2 times 0.016. So this puts us at 0.532. So 0.534 is beyond 0.532. Therefore, it is statistically significant. Therefore, it would be unusual to find a sample with 534 out of 1,000. Did I math it correctly? Okay. So it would be unusual to get this right here. That would be unusual. Therefore, this would cause us to reject our null hypothesis. So I'm going to draw the picture, and I'm sure that all of this is in slides after this. You just watch. I'm basically doing it all over again. This is a right-tailed test because our 0.5, our 534 is bigger than 500. So what I'm looking at is, does my sample land in here, or does my sample, I'm going to do a different color highlighter, land out here? This would be fail to reject. This would be reject. That's what would happen. This right here is my 2 standard deviations away. Because I wasn't given an alpha, I'm just using the 5% right now. So that would be 2 standard deviations away. This, the 0.534, it's just right outside. It's like right here. This is 0.534. Therefore, it is in the critical region. That's what this is called, critical region. This is the critical region. If my sample lands in the critical region, we reject the null hypothesis. Questions before we move on and I do a little bit more. Okay, I'm gonna move on. I'm gonna pop over the next screen. See, look at this. This is just 1 standard deviation away though. So, okay, so you may consider sample evidence to be significantly statistically significant or sufficient if we are too many standard deviations above the population. I just said all this. Let's move on. So instead of adding 2 standard deviations to it, they found the z-score. Our z-score is 2.15, which puts us beyond that 2 standard deviations, because our textbook likes to just make everything z-scores. To me, that looked like harder math than just adding 2 standard deviations, didn't it to you? This is harder math. So we reject the null hypothesis because my z-score tells me this is more than 2 standard deviations from the mean. So I can write a nice, oh, it doesn't say it. See here. I thought that there was a conclusion. I guess there's not. Okay. So the what did this do? I don't like this. So what this did was it asked me the probability. So this area and out here is 2.28%. The z-score of 2 gives me 2.28%. Because remember, our middle, so we have 2.5%. This is what our estimate was. But as we know, the empirical rule is not exactly 2.5% in each tail. The empirical rule was kind of like rounding it. So actually 2 standard deviations gives me 97.72-ish% in the middle, and then, or to the left, it gives me this much in my tail. Oops. So anything landing out there is going to be statistically significant, because the probability of landing in that tail is only 2.28%. I don't really like the way that they do it because they use z-scores, and I don't really like z-scores all that much. Okay. Hey, look, this is even better. So this shows me this is the math that I did earlier. This is better. This is the math that I did. So anything that lands out there has a 2.28% chance of happening, and therefore it is statistically significant. It's going to be so much easier when we're mathing it out, but we got to do all the background stuff first. Okay, we're moving on. So the classical approach, there's two different ways to test your hypothesis. So we have two different ways. One way is if my sample proportion is too many standard deviations from what we are given in our null hypothesis, then we reject the null. So we have our critical value. You guys remember the critical value? We saw that on the Z table. So when we had our, I'm just going to, you remember these were critical values right here when we were doing our confidence intervals? Remember that? Those were critical values. This would be the positive critical value, and this is the negative critical value. This tells us how many standard deviations above and below our mean, the edges of our confidence interval were. So what you're going to do is you're going to take your sample and you're going to find its z-score and you're going, or t-value, but you're going to find its z-score. You're going to compare it to the critical value. That's exactly what this is. If my sample is too many standard deviations away from the mean, or it's beyond the critical value, has a larger standard deviation than the critical value, then we will reject the null. So that's just comparing the critical values. Next, this is the other way. So I'm going to leave this alone and we're going to just go here. So I'm going to go over here. I'm not. This is it. So the p-value approach, instead of using z-scores, I'm going to find the probability of getting our value. So like, for example, so I would say in that last example, I would say the probability that I got a sample, was that an X bar? No, it was a p hat. The probability that my p hat was greater than 0 point, what was my, whatever my, and whatever my alpha is. So let's say alpha is 0.05. This is my, let's say this is my alpha. Alpha. Okay. So, or this is poorly, back that off, erase it. This is not alpha. The probability that I got a p hat that was whatever my 0.534. This was my p hat. Sorry about that. This is the p hat that I got. So I want to know what's the probability of getting that or equal to that. Okay. Sorry about that. I like total, my brain just kind of fogged for a second. So this was my sample. This is the sample that I got, and I'm looking for the probability that I would get that sample or larger. If whatever my alpha is, if that probability is greater than alpha, I would fail to reject. If that probability was greater than alpha, if that probability is less than alpha, I would reject. So let's say I have an alpha of 5%. So I have my alpha, my statistic, what did I call that? So what if my alpha is 0 point, oh my gosh, stop it. My alpha is 5%, yet the probability of getting my sample was 2.3%. I would reject the null hypothesis because that probability is less than alpha. However, if my alpha was 5% and the probability of getting my sample was like 8%, I would fail to reject. So this is just comparing the probability to alpha. And we call that a p-value. This is going to be so much easier once we're using numbers and we're actually mathing it out. Trust me, it gets easier. So we can compare the p-values and we can compare the z-scores. We would never compare a p-value to a z-score or a z-score to a p-value. All right, that was it. That's it. I'm just telling you the two ways we check it. And there we go. You don't start section 2 because we haven't mathed anything out yet. So on Thursday, we will math out and you'll see comparing with the p-values and comparing with the critical values. It's going to make much more sense. This just lays the groundwork. You can do 10.1 and you should be able to do that and do that well. So before I stop the recording, any questions on the recording? All right. I'm going to turn the recording off. Stop.